for the introduction. As was mentioned, I work at Loughborough University in the UK. So in our research group, we work mainly on computer vision, on image analysis. We also do some work on computational intelligence, pattern recognition, pattern classification. And one of the particular areas that we've been working on for quite a number of years is image retrieval. And I'll try to present you a little bit of some of the stuff that we've done there, in particular trying to actually perform image retrieval of compressed images very, very fast. So let's start. When we're looking for something, looking for information, particularly on the internet, so we usually turn to a search engine. So we turn to Google or we turn to something else, and we type in what we want. If we want coffee, we type in coffee. And we're now trying to do the same for images. Actually, many of these search engines allow you to search for images as well. So you can go to Google, you can search for images. So just go to the selected image tab there. You can type in coffee, and what you get is, for example, is this here. So what I was looking for here were a couple of images of a nice cup of coffee. But of course, coffee is quite ambiguous as a search term. So I get a couple of images like I wanted. I get some images of like coffee beans and so on, which again is understandable. And I get a couple of, like here down, we get a laptop, get a couple of outliers, odd images, which don't really match to my query. Now, the thing is what Google is doing behind the back, basically, it's performing the search fairly similarly how it's actually conducting normal searches, so when you're searching for text. So the retrieval results here are actually not based on the images themselves, but they're rather based on the image file name and on text that is surrounding the images in the HTML page. But in particular at Google, one interesting thing that we can do is we can, so if I hover over one of those, because I thought it was already loud enough, is it? Okay. If you hover over any of those images, so you get like a larger version, and I just blow it up so you can actually see it better. Because something quite interesting is there, we've got a link which says similar. Now, since it's a link, I can obviously click on that, and what I get now is I get a second set of search results. Now we see we get lots of nice images, and what Google is doing here is what we call content-based image retrieval. And that's kind of lead basically to my talk here. So what is content-based image retrieval? Basically means we have just the images, and we're trying to extract some information from the images. So we extract some image features, and then we're using those image features for performing the search. In particular, what I've done here is I picked one, what we call a query image, the one at the top here, and I was looking for visually similar images. So we use those features and we try to look for something similar, means images with similar features. Now there are lots of features that the content-based image retrieval literature is huge. Thousands of papers started back in the early 90s, 1991. So actually the very first work that kind of kicked off that whole area is that well-known paper, Color Indexing by Swain and Ballard, where we basically says we can search by color. Color is very, very useful, and the way that we can do it, we can take an image, we can calculate a color histogram, so kind of frequencies of the colors in the image, and we can use that as an index, we can use that as a feature, and we can then search based on that. Particularly what we can do is we can do what we call query by example. That means we've got a database of images, potentially very big. For each of those, we can calculate a color histogram or some other features. And then we have a search, means the user gives us an image, says, search for something similar, and we're extracting the features from that user image, that query image, and then we're comparing those features to the features from the database. And then we're ranking everything, and then we're basically getting what I've shown you before, namely those search results by sorted by visual similarity based on those features that we're extracting. So that's, works quite fine, lots of work in there, lots of very advanced work in there, but still, there's one problem, namely that essentially all the images, or virtually all the images that, for example, are on the web or that we've got at home and so on, are automatically compressed, because there's still limitations, in terms of bandwidth, in terms of storage space, and so on. And almost all these images are compressed using JPEG. JPEG is, very, very dominant as a compression technique. Now, why is that a problem? It's a problem because virtually all the image retrieval techniques essentially work on pixel values. So they work on the uncompressed image, which means that if I want to actually extract the features, if I want to perform image retrieval, I need to decompress the images. I can then extract the features, and then I can do something with those features. So that's not ideal, and therefore what we would rather like is something that is called midstream content access. That means that we could, what we want to do is we want to perform that processing, be it image retrieval, be it something else, directly in the compressed domain of the images, without the need of decompressing them. And there are basically two potential solutions to that. One is we actually devise some new image compression techniques that allow for that, and we've done some work in the past on that as well. The other one is, because all these images obviously exist already, mostly in JPEG, we try to do something that actually works in the JPEG compressed domain. And that's what the focus basically of my talk is going to be. So in order to be able to do that, we first need to look at, how does JPEG actually work? So I try to run very, very quickly through how JPEG works as a compression technique. So we start with an image. Nowadays, it's typically a color image, which means that we've got 3 different channels, RGB. We all know that that's not the best way of actually storing the information. That's purely because that's how we are capturing the information. That's why we store it like that. So in JPEG, we first transform that data, and we switch into a different color space. Particularly, we switch into usually the YCBCR color space. JPEG as a standard actually does not define a particular color space, but this is what typically happens. Now, what it means is that we can separate the luminance information in the Y channel, and we've got 2 chrominance channels which effectively have got the color information. Now, things in the color domain change not so quickly. We can't really notice that much. So one thing that we can do is we can essentially downsample the chromaticity channels to immediately perform some form of compression in a sense and reduce the bandwidth. So typically we downsample that by a factor of 2. So we have one full-scale luminance image, the Y channel, and we've got downsampled versions of the chrominance channels. What we do then is we take each of those channels individually, and it's individually processed and compressed. We take that image, divide it into smaller blocks, 8 by 8 blocks, and then we switch from the spatial domain into the frequency domain. Reason is that we can essentially perform the compression better in the frequency domain. Here in particular, JPEG is based on the discrete cosine transform, so we switch from 8 by 8 pixels to 8 by 8 frequencies, or BCD coefficients, as I've got it here. So that transform is lossy, but then we're performing some selective quantization afterwards, where we're essentially throwing away more of the high frequency information, and we retain more of the low frequency information because it's more important. Afterwards, that quantized data is then entropy coded, and we distinguish the DC term so the very top here, which basically captures the average of each 8x8 block, that is differentially coded, so difference from one block to the next one, or the previous one rather, and the other, the AC coefficients, so the remaining ones, are run length coded, because there are lots of zeros, after having gone through a zigzag transformation, and at the end everything is Huffman coded, so using Huffman tables. So it's quite reasonable, complex. What it means here, I've got again all these stages through which we are going essentially. At the end we've got a compressed image. Now, if I want to perform image retrieval from or on a JPEG image, if I want to extract features from a JPEG image, it means that I need to undo all these stages to get back to the pixel domain, to the uncompressed image. So I have to undo all this. In particular, there's the inverse discrete cosine transform, which is the kind of crucial part in terms of computational complexity. So that's the part that takes the longest. So it's not that efficient to actually do that. So what we want to do is we want to do something that basically works faster. So we want to do compressed domain retrieval, which means that we want to access the data not here, but somewhere earlier, ideally before that inverse DCT. So compressed domain techniques for JPEG would try to get the data from here, and so that's the dequantized data that we've got at this stage, so dequantized DCD coefficients. So we would need to try to make sense basically of that kind of data there to see whether we can use it for image retrieval. So let's see how we can do that. One of the, in a sense, simplest things that we can do that is, I've mentioned that we've got, for each 8x8 block, we've got one DC term, the rest are AC terms, and the DC coefficient, the DC term, describes essentially the average of that 8x8 block. So what it means is that if I just consider the DC terms and I ignore the rest, I essentially have kind of a downsampled image, because I've got the average of each 8x8 block, so I've kind of got a smaller version of that image. But I can actually have that directly in the compressed domain. I can access that directly. So that's quite useful. So I can use that directly for example, building something like a color histogram. The other thing that I can do is I can actually try to separate color and texture data, because we've got that separation in terms of the color channels. So color usually relates, projector's not very bright, usually relates to the chromaticity channels. Texture is something that we usually extract from the grayscale channel, from the luminance channel. So we use the Y channel for extracting some information on texture, shape, and we use the other ones for extracting information on the color. And we do that based only on that DC data. So the color information is quite simple. I can take directly the DC coefficients and I can build a histogram. Very, very similar how we will be building color histograms. So here I would get again, you don't see very much here on the image, but at least you see the histogram. We get a two-dimensional histogram basically, because we've got two color channels. On the texture part, we can, again, kind of see that as a smaller version of the image, and we can try to extract some texture information from there. So what we did, we used LBP, you might know local binary patterns, very popular, very fast, simple method basically, and usually gives very good results for describing texture and therefore also for texture classification, texture retrieval, and so on. So we run LBP on the DC image in a sense that we are getting. I'll skip that, that's just a transformation that we do beforehand. So it means we've got color information, effectively kind of a color histogram, and we've got some kind of a texture histogram. We've got both of these kinds of information readily available in that JPEG stream, and we can therefore perform image retrieval based on a combination of color and texture shape in that sense. So we did that, and we did some experiments on essentially a benchmark database where it was quite important that we actually captured that database in the uncompressed state. So afterwards we can see how things basically change with respect to compression. And the very nice thing here is that we can see how well it works. So here results are presented in terms of what is called average match percentile. It's basically a number from 0 to 100, where 50 is essentially as good as guessing, 100 is perfect, so the higher the better. And here's what we're getting from our technique in the JPEG compressed domain, and here a couple of very, very well-known benchmark image retrieval techniques, some of those MPEG-7 techniques that are commonly employed in various systems. And we can see that we get very, very similar retrieval performance. And the other thing that's quite important here is we can see how computation intensive it is, both in terms of the extraction, so the feature extraction, that's here the part where we've got huge, huge differences, and then also in terms of the comparison as well, which is essentially a function of the feature length. But the really important part here is this one here, coupled with the retrieval performance as well. And we can see that indeed we can perform retrieval or feature extraction much, much, much faster compared to the other ones, because conventional techniques need to first decompress. So much of that time here is taken up by decompressing the image in the first instance. What else can we do? So this is where we kind of started. So this is from quite some time ago, our kind of first work in that area. And then we looked further, and in particular interested in trying to access that JPEG data closer and closer to the actual JPEG file. So the next thing is that we were trying to not have to do the dequantization that would happen. So when we're looking again at how the DC coefficients are coded, I mentioned that they're differentially coded. That means they're coded as a difference of the value to the value from the previous 8x8 block. So we have got difference data there, and we thought that that information essentially should also be quite useful for performing image retrieval, because differences again is something that actually relates to kind of texture information. It also relates to the image gradient that we've got in there, and it also gives us some information about, for example, about uniform areas. If the difference is over 0, everything is the same. So what we thought is, okay, let's do that. Let's actually take the difference data directly and use that as a feature. And again, we're doing that in terms of histograms, which are now not uniform histograms, but they are non-uniform histograms. So what it means in terms of that figure that I'm using all the way through is that rather than here, we're now accessing the data here already. So again, less effort in terms of decompressing and faster. In the end, we don't need to undo the dequantization, or we don't need to do the dequantization, undo the quantization, I would say, and therefore we should be able to speed things up further. We've done that in terms of feature extraction. So we get a small kick basically again in terms of the speed here, and here we've compared it with that texture method that I showed you before. We also see that we actually get very, very useful information. In fact, we got better results here on this one than we got on the LPB data that we used before. And then the other thing that we can actually do is we can then combine that again with color information, those DC histograms that I've mentioned before. We can see how we can combine them in the best way. And then what we did, we kind of did a benchmark on different standard techniques. So in the pixel domain of a whole bunch of techniques that also perform image retrieval in the compressed domain, and then we compared it to our method that we got there. And at least to my knowledge, at the time when we published that, we had like the best performance basically of all these techniques. And we also had something that is very, very competitive in terms of the computational complexity that comes with it. So that's quite interesting, I think, but we didn't actually stop there, and we thought that we want actually something that supports what we could call online image retrieval. So what do I mean by that? Well, first, this is the kind of standard scenario of image retrieval. So we've got a database, potentially very, very large database. We extract our features, and we basically store the features again in the database. When we then perform retrieval, query by example, we've got a query image, we extract the features from that, and then we compare it to the features that we have stored in the database, because we don't want to have to do that part again, of course. And then we get our results. Now, in what I call online image retrieval, that isn't really possible. So here, rather, the extraction part is, part essentially of that pipeline that we've got there. So we've got our query image where we extract the features, but also the image collection that we've got, again, we need to extract the features on the fly. So if we want to do image retrieval from, for example, images from Flickr. So only Flickr can basically do what I described before. If I want to do it, that's the way that I basically have to settle for. So I have to extract the features from the Flickr images on the fly, and then I can perform my image retrieval. Now, of course, here it's much, much more important that we can actually do something that is, extremely fast, because otherwise, even performing retrieval on, a couple of thousand images will just take too long to get an interactive response. So what it means is that even, those techniques that I've mentioned before, even though they operate in the compressed domain, they're basically too slow. They're too slow because we still need to essentially retrieve the file, read the file, and extract features now from the compressed domain, but it's still, that overhead associated with that is still quite large. So we thought, that we can actually do something about that. Now, what we came up with is that in the end we can, as we'll see later on, we can perform extremely fast image retrieval because we can actually make use of data that is stored in the header of JPEG files. What that means is that in order to perform that kind of online image retrieval, I don't need to retrieve the complete files. I just need to retrieve the header, so a very, very small portion of that, and then I can use information from the header for actually performing the retrieval. And that will obviously be significantly faster compared to anything else. So how do we get there? For that, again, I need to dig a little bit deeper into how JPEG, particularly the later stages of JPEG compression work. So I've mentioned that we have got the DC data, so we've got 8 by 8 DCD coefficients. One of them is the DC term, the other 63 are the AC terms. The DC stream, as I've mentioned before, is differentially coded. The AC one is zigzag coded, and then then run length coded. At the end, both of these are entropy coded, so to maximize compression, and usually this is done based on standard Huffman coding. The thing is that in order to actually not have to do the Huffman coding for each image during the compression stage, JPEG has essentially defined some kind of standard Huffman tables. But as a user, we have got the possibility of defining our own Huffman tables, essentially maximizing decompression, so minimizing the file size, and that is actually something that is being done by companies like Flickr and so on. So what it now means for us is that we can actually have these individual Huffman tables, and the Huffman data basically is, in a sense, adapted to our image. What that means, again, is that the Huffman table actually tells us something about the image. And I give an example of that. We've got 4 images here. Obviously, these two are very similar. These two are also very similar, but the two groups are very, very different. So when we're now looking at the Huffman tables that we can get, so this is one set of the Huffman tables that we've got in the file, and even visually you can see that these two tables here, these ones here, are very similar, and again, they're quite different from each other. So the idea that we had was, in a sense, very, very simple. So I thought we can actually use those Huffman tables directly because they're adapted to the data, means adapted to the image, and therefore, specific to that image, and they will tell us something about that. In a sense, when we're looking at that DC differentially coded data that I've mentioned before, the Huffman table is, in a sense, a kind of compressed version of that, if you want. So what do? We take the Huffman tables directly, and we compare the Huffman tables for actually performing image retrieval. Now, what does that mean in terms of our diagram? So again, here is the compressed version of that file. Here is the Huffman table, and here is basically what we're retrieving. The Huffman table is coded into the header of the JPEG files, so I can retrieve it directly from there, use it directly from there for the purpose of retrieval. So we then thought, there are different norms that we can use, how actually calculate similarity between them. So this was based on a simple L1 norm, basically. And we can take advantage of both luminance information and chrominance information, because there's one Huffman table for the Y channel, and there's another one for the CBNCR channels. And we can also weight it towards chrominance, which is more interesting here, usually gives us better results. So we can then see again, based on that same kind of benchmark that I've shown you before, how well that works. Again, we've got some pixel domain techniques, we've got some compressed domain techniques, including the one that I've mentioned before, and now we can see Huffman tables, how well that works. So we see it gives us 84 compared to 90 roughly for the other ones. So it doesn't quite match the retrieval performance of the other techniques. That's maybe not so surprising because it's very, very small amount of information that we're using here. But the huge difference is here the query time. So here there's an online image retrieval scenario. We've got a query image. We want to match it against a database. This was, I think, the database of about 1,500 images. And this is the time that it takes to perform that. Means, comparing it to all the images in the database, for each image extracting the features and performing the feature comparison. And here you see a huge, huge difference. That's a couple of orders of magnitude difference, because here we're just retrieving, the headers, and we've got the data directly there. There's no need to retrieve the remainder of the file. There's no need to perform any kind of decompression. There's no need to perform any kind of feature calculation afterwards. Everything is there readily available. And we can do that based on, we can retrieve data from Flickr using that. Still, the one problem was that, this wasn't quite that great. But then we looked further, and we have Huffman tables not just for the DC data, but also for the AC data. And same kind of thing, basically, that we can see. Here's again the same images that I've showed you before. Not quite as clear to see here. So those tables here are much larger than the DC ones, which are quite small. But still, it kind of holds that similar images give us similar tables. So we kind of expanded that concept, and we can perform retrieval based on both the DC data and the AC data, which gives us essentially information about texture and other things and so on. So we can actually integrate those both into one approach. Doesn't really add much in terms of the computational complexity, because both of those tables are part of the header, so it's just the comparison which takes slightly longer. And we can again run the experiments, and again, all the stuff that we've basically seen before. Now we can see how well the AC tables on their own basically work, and we see that again, that's quite useful. and then we can put both of them together, and now we actually are reaching a retrieval performance that is fairly similar to those that we're getting from typical compressed domain techniques and typical or very, very popular pixel domain color-based techniques as well. And we still have the same huge advantage in terms of the retrieval time. So again, a couple of orders of magnitude faster. We can't do that kind of online image retrieval with any of those techniques, well, not practically, at least. I can show you one retrieval result. So here's a query image. Here's what we're getting from various techniques in terms of the first 10 images or so that the top 10 retrieved images. So this one is a pixel domain technique. This is a compressed domain technique. This is what you're getting from the Huffman tables based only on the DC data, and this is the combined method. And you can see that we get in the first couple of images, we get one match here, one match here, one match here, one match here. Fairly similar again to what we are obtaining from the other techniques. We've then scaled that further. So these that UCID data set has got about 1,500 images. And what we've then done, we've essentially expanded it. So we've mixed it with there's a 1 million data set, the Flickr 1 million data set. So we've now got a combined data set of just over 1 million images. And we can see how well the retrieval performance basically scales. And we see that actually it scales very, very well. In fact, it actually scales better than most of the other techniques. Ours was up, some of the others actually go down in terms of the retrieval performance. And I haven't got it in this table here, but we still have got, of course, the same kind of thing in terms of retrieval time. These here now takes a huge amount of time, downloading 1 million images, extracting or uncompressing it potentially, extracting the features, performing the retrieval. Here we're just downloading the headers. It's reasonable, at least, in terms of the response rate. And here again, an example of what we're getting in terms of one particular sample image and a couple of retrieved results. And again, we're getting the same images pretty much in the top 10 images or so, what we're getting. So we can perform image retrieval very, very fast based on information that can be encoded directly into the JPEG header information that we've got there. There's one other thing that is also part of the JPEG header, and we have these Huffman tables that I was just talking about before. We also have got quantization tables in there. Because I mentioned at the beginning that in JPEG, that quantization is kind of selective. Higher frequency information, we discard more. Lower frequency information, we retain more. And that, how we're doing that is encoded in a quantization tables, which are 8x8 tables. Again, by default, there are standard tables from the JPEG consortium. And again, if we wanted to, we can actually tune those quantization tables. And what that basically means in terms of tuning those quantization tables, so there's a particular method of doing that, it basically gives us better looking compressed images. So it might not be that visible here on the projector, but as you can even see, especially in the background. So here's what we're getting with standard JPEG, and here's what we're getting if we actually optimize those quantization tables. So if we get actually slightly smaller image size in this case, so we can compress more, but we get image quality that is superior to what we're getting here. Because again, it is adapted to that particular image. Now, you might be able to guess already what we thought then. If we have got quantization tables that are now adapted to the images, and quantization tables again that are stored in the header of the JPEG file, well, we can actually do this essentially the same what we did with the Huffman data. We can see whether those quantization tables themselves are useful, and indeed they are. So here I've got again an example, 4 images, 2 pairs, And here's what we're getting from the quantization tables. Again, there's one quantization table for luminance data. There's one for the chrominance data. And here we just code the numbers, of course, but I'm just showing them here graphically. So again, when you look at that, we see that we get very, very similar tables here and here, and that the pairs are quite different. So we can perform or use similar kind of idea again, very, very simple. We can use that data directly, use the quantization tables directly for the purpose of image retrieval. That again means that we access just the header basically of the JPEG file, because that's where the quantization table is essentially stored. Again, we can think, how do we do that comparison? Again, here we do actually a simple L1 norm between them. And again, we can think, how do we favor chrominance compared to luminance? And we can again see how well that works. Same kind of comparison that I did before. Again, some pixel domain techniques, some JPEG compressed domain techniques, and what we did here, again, results in terms of retrieval performance and in terms of retrieval time here for that online image retrieval scenario. We see again, it's very, very fast, as fast basically as the DC, the Huffman table technique. Doesn't quite reach the performance here, so those quantization tables are a little bit trickier, but we still can get fairly useful results as such. So here's a comparison of when we're searching for this toy here, what we're getting with a typical pixel domain technique. So top 4 ones were matches, compressed domain gets slightly worse, ours then still gets slightly worse, but it's not terrible. And again, we can see where that scales, so we can run it through a larger database, and we see that it scales quite well. Actually, it kind of closes the gap to the other algorithms in terms of retrieval performance. Still might not quite be good enough for actually performing pure retrieval as such. But one thing where we have essentially used it is as a kind of a filtering, first stage filtering in an online image retrieval scenario. So we basically first use this technique here, run it over the complete database, sort the images by similarity based on the quantization tables. Then we're taking the top n images, n might depend on the database, could be 100, could be 1,000, and so on. And then we're using a better technique basically on those. And the other, million images or so, we don't look at again. So we kind of re-rank the results after that first filtering, and then we get to something that gives us effectively the same retrieval performance as the, very well working pixel domain techniques, because in that filtered subset that we've run through in our first stage, we typically retain all the important images. We're then re-ranking them based on the second technique, then we get the same performance. This is essentially what this one here is showing. I think I've pretty much out of time. It was about 40 minutes, I think. So apologies if it was a little bit too fast. I was just trying to kind of squeeze in as much as I could. But just in summary, so I was discussing compressed domain image retrieval techniques, specifically here for JPEG images, because there's some statistics which say that of all the images on the internet, about 95% or so are JPEG images. So it makes good sense to essentially focus on that. And I've shown you kind of successively how we're trying to access that data closer and closer to the compressed version, basically, the compressed file as such. So showing you how we can first exploit DC data, so we don't need to undo the discrete cosine transform. I've then went one step further back in a sense, where we don't need to undo the dequantization, so using the differentially coded data directly. And then the last two techniques, which I think are quite interesting, because here we're actually able to perform image retrieval from information that can be stored directly in the JPEG header, and therefore doesn't really need any sort of decompression at all. So I hope it was interesting, and just put up my details here. And of course, any questions, any comments that you've got, I'll be trying to answer those. So thank you very much for your attention. Thank you.